International Conference on Natural Language Processing. I'm Zhang Yu. I'm here to present our research regarding OOV terms. The title is OOV term translation, context information, and definition extraction based on OOV term high prediction. This work was done by Akira Shimazu, Noemi Lin, and me. We are from NLP Lab, Japan Advanced Institute at Science and Technology. So let me begin our presentation with a simple outline. Firstly, we would like to explain the motivation and introduction of what we do in this research. Secondly, we will give some existing approaches. And thirdly, we will propose our approach and explain our methods. Fourthly, we will explain the experiments and the results. And finally, we will conclude this research. So basically, what is OOV terms? Our vocabulary terms cannot be found in most dictionaries. They are typically new terms from current appearance, such as personal names like Obama or Bush. According to our observation, there are two types of OOV terms. One is very commonly used in newspapers, articles, and daily events, such as we call it name type OOV terms, such as personal names, place name, and brands, etc. The second type is technical type OOV terms. They are usually the technical terms of some new knowledge, some new disease, or some new medicines. However, different types of OOV terms tend to translate differently. I would like to explain something that we observe in our research. We call it hyper translations. Name type OOV terms prefer to use transliteration. So most of the name type translation is using the sound, the vowels of the sound, and using the similar characters from the target language. And the technical type OOV terms prefer to use transliteration plus dictionary, because some of partial of the terms in the source language can be found in the dictionary. And some of them has a meaning. So they use a combination of dictionary and transliteration. So hyper translations are translations of OOV terms use part of original OOV term. For example, we have a disease. This disease is taken from the ICD-9. It's called the International Classification of Disease. And it's a Kenny-Copy syndrome. And we have the Chinese translation over there. Actually, the Chinese translation, part of them is English characters. So it's English alphabet, it's not Chinese character. And most existing system does not solve this kind of problem. So I would like to give some we call it existing problem one. In here, we have 5 OOV terms. They are all technical type, and they are all disease taken from the ICD-9. And the correct Chinese translation conducted by human is in the second row and second column. And the last one is the result generated from 2 of the very famous systems. One is from Zhang and Vince in 2004. It is so far the largest citation for the OOV term translation, especially from English to Chinese. And we can see that the existing system tends to ignore the hyper translation, the part that is not Chinese characters. So we conclude that the existing approach may give an error in translation. And our motivation one is that we will try to handle the hyper translations. Another problem with OOV term is that translations are OOV terms as well. For example, many existing approaches have found many ways of finding translations for OOV term. However, the translation of the OOV term is just another OOV term in the target language. For example, here, so translation provides very little information to users. For example, we have English as a source language, my waist, and here is the translation in Chinese, and this is the translation in Japanese. Without knowing what, who, or is my waist, we do not know. Just by judging the translation itself, this can be a brand of clothes or jewelry, or even a shampoo brand or cosmetic. We do not know that. Let me give you a simple example to wake you up. We have two persons and chatting on the computer. Suppose they are from different country and using different language. So one of them probably using some kind of translation tool such as Google Translate, and one person suddenly types something such as my waist, and the second person uses a translation tool and gets the Chinese translation. However, the first person knows that my waist is a famous actress. The second person is thinking of a shampoo that is currently localized, using the same name of the brand in that country. So the existing problem too, that we took three OOB term here, and we're still using the existing system to generate the translation. And we can see that for the first two, the translations are correct. However, it does not provide any idea or meaning of like what is my waist, is a person, it's a brand, or it's a company. And the second one, we can guess from the characters, from the Chinese characters, and we can guess that probably this is a disease. But do we know it is a heart disease, a skin disease, or neuromatic, different kind of whatever disease? And the last one, first translation is a Hebrew translation. The existing system simply ignores the English part and give us a partial translation. The translation itself is wrong, and also does not give any meaning of what are those diseases. So from the above example, we can see translation offer little knowledge or information for user. So our motivation too is that we would like to extract additional information for the user to understand what are those terms. So before I go to our approach, I would like to take a deep methodology. We look deep in methodology of the existing method. So generally speaking, OOB terms can be translated by three methods. They are human translation with field of specified knowledge, automatic translation from parallel corpus or comparable corpus, and the last one is automatic mining from the internet. Most OOB terms have their corresponding human translation nearby on the internet, and this is one of the systems that has been recently adopted by many researchers. And the advantage is that the database is expanding, it's renewing itself every day, so the new terms that appear can be found. And basically it has three stages in the automatic mining, wave retrieval, translation extraction, and translation selection. Once again, however, translation mined from internet in another language are also OOB terms, just in another language. So I will explain how does the wave mining do in the 30 Chinese characters, basically 30 target language characters. So once they have extracted those strings, they try to generate the possible translations. There are a lot of ways, such as one of the ways that they can cover all of them is brute force, simply generate all the possible substrings and the strings, or the extracted strings. And from that one, they have to select the correct translation. Many methods has been proposed. Lens, concurrence, hierarchy, or local maxima, or machine learning has all been used, and some of them has advantage in some data and some of them have. So it's not like always the best. So what does our method do? For the existing method, we compare here that we take two OOP terms. For the existing method, it does give the translation. The first one, MyWays, it does give the correct translation in Chinese language, and it is correct. The second one, Lens disease, the translation is wrong. And for our method, we provide the translation, not only the translation, we also provide the definition in English, and we also provide the context information. By here we call context information is basically semantic information. The information that can be easily identified, like what is this term? For example, here we can identify that MyWays is kind of American. It's a playwright, it's a screenplayer. So we can identify this. She is a person, and for this one, we can identify that it's a neuropathic and nerve system related syndrome. So we provide information for users to understand the OOP. So from this slide, I will explain our approach. Basically, our approach is developed into 5 steps. They are the snapper retrieval, the snapper ranking, and the definition selection, the multilingual context information extraction, and OOP type prediction. And then we have the name type OOP translation and the biomedical type translation. The reason why we have to do the prediction is that we studied this research as a translation for the biomedical terms. However, after we developed the system, we see that there are some drawbacks when we apply such system for the name type. And the existing system is very successful on the name type. So we basically use our system to predict the type of OOP term first, thus different types of OOP terms can be translated using different methods. And from the snapper ranking and the definition selection, our result will be the English definition. And from the context information extraction and OOP type prediction, we will get the context information or the semantic information. And from the translations, we will get the OOP translation in the Chinese language. And in the snapper retrieval, it basically contains of snapper retrieval for the definition and translation. In the snapper ranking and the definition selection, it consists of integrated ranking and web statistics. In the context information extraction and OOP type prediction, we use a WordNet and a multilingual dictionaries. And for the name type OOP type translation, we adopt the existing method. And in the biomedical type OOP type translation, we use there's 2 more steps. It's a candidate extraction and a candidate selection. In the candidate selection, we use adopted rules and translation extraction. And in the candidate selection, we have feature extraction and translation filtering, and finally we use machine learning to select the correct translation. So let me begin with the first step. Is a snapper retrieval for the definitions. Let us illustrate it with a simple example. For example, the input is OOP term. The snapper retrieval simply curate through the search engine. For example, here is a Ford, and we will retrieve the English snippets, for example, Ford. So here is a good example that we retrieve the definition of a Ford company, Ford Motor Company. And then the second step is the snapper retrieval for So the third step is snippet ranking and definition selection. According to our observation, many OOB terms have their definitions on the web retrieved snippets. The problem is how to differentiate the snippets with definitions and snippets without definitions. Statistically, the majority of retrieved snippets contains no definition. However, the snippets with definition possess some patterns. For example, my waist was a American actress. So according to our observation, certain verbs can be used to find the snippets with definition. We propose to use a rule-based ranking, and together with the verbs and location, location in terms of verbs and OOB terms. Furthermore, search engine, many good search engines hire a human to do the ranking of the snippets of the web pages. So usually when we search certain terms, the one with a high search engine rank are usually ranked by human, and usually they are very with a high quality and could provide the definition and the context information of the terms. Thirdly, during our research, we found out the web page, the web data that provide good information or good result are usually government, organizational, education, or those web pages provide better information than company or profile or net. So we use domain ranking as well. So combining all of those, we do our snippet ranking and definition selection. Here I provide an example of our snippet ranking. So we use the same example, my waist. So we can see SWR stands for the ranking result of our algorithm. SR is a search engine ranking, and DR is a domain ranking. So basically, we will only select one result, which has the highest ranking, is 111 here. It's actually from Wikipedia, and it provides the information like who or what is my waist. And for the next step, once we obtain the possible definition, we have to try to extract certain terms that can be easily identified by our system to do further research. So we call it the context information extraction and OOB type prediction. So in this step, we extract the context information from OOB terms. We construct the two-terminated trees from the WordNet, and we use some supernode noun terms from the WordNet, such as country, occupation, and for the biomedical terms, we use such as like illness or sickness, and then the OOB terms are predicted by the number of the context terms found in the definition. So for example, if we get like my waist, and in our definition we have like American actress, playwriter, so those terms identify that my waist is a name type. And context information are then translated into Chinese language multilingual dictionaries. This is just a simple example of the word. So the next one is a name type and the biomedical type translation. So name type is done by the existing method from Zhang and Mills, the ranking, the alpha ranking method. Basically, they use a core frequency of the term and with the target term and the source term, and with the length of the term. That method is very successful on name type of returns. And the biomedical type are developed into two more steps, with the candidate extraction and candidate selection. So in the candidate extraction, we take the retrieved snippet and regular expression rules plus our OOB term as input. So we make new rules, we call it as adoptive rules. Once the adoptive rules change the original regular expression rules, we do the candidate extraction, and hopefully we got the possible translation, and then the output are the possible translations. I have an example here. For example, we taking the alpha-1 anti-spin deficiency. Over here, this is one of the source term back to the internet to collect some kind of wave statistics. And once we have all of them, due to the fact that there could be a lot of noise when we use a brute force to generate a candidate. So we use certain statistics such as location and the frequency, core frequency, to rule out some possibly wrong candidates. We call it filtering. Once we've done filtering, we train and apply a Bayesian net with AWS internal fault cross validation. And here we have the correct translation. So features used in our approach. In this approach, we used up to 21 different kind of features. I will explain some of them, such as modified association measures, exact location distance between each translation candidate and its English term, core distance. I think that is simple and chi-square, semantic condition probability, core frequency of translation, and English term length similarity. So we will only explain partial of the features used due to the time restrictions. So modified association measure here, the difference that we try to modify the association measure is that we recurate certain features back to the internet to get the wave statistics. However, the wave search engine does not provide the total number of the web pages in the world. So we can only assume that how many web pages are there in the world. So we assume that the total number of the web pages is much, much larger than the number of the web pages that contain the translation of the outer vocabularies. So we modify the association measure, and it basically does not require n, which is the total number of the web page. However, for the traditional chi-square, it does require n, and that we can only do such kind of feature on the local datasets. So from here, we will explain the experiment setup and the evaluation scheme. This flowchart is the same with what we have in our initial flowchart. So the difference and the input here is 4 different categories of OOV terms. Top 500 companies, famous people, car, brands, and the city code names. And in addition of those name types, we added the biomedical type over here is the ICD-9 CM. And the output are 3 different parts. For the English definition and the context information in English and Chinese, there is no correct result. So we have to compare it with human search results. We hired 2 graduate students to search it and then rate our results and do the evaluation. So that is our performance for the English definition and the context information extraction. For the OOV term translation, there is a lot of existing methods. So basically, first we compare with the list that is provided in Chinese language. And then we compare with 2 different existing state-of-art existing methods. And then that is our performance for the translation. So this page shows the experimental results for the context information extraction and the definition extraction. As we can see that name type has gained very high result than the biomedical type. Due to the fact the biomedical terms, some of them has very low recall from the web search So we propose to integrate a ranking approach for extracting the monolingual definition and the multilingual context information of the OOV term. And our ranking approach predicts the type of OOV term and apply different methods for different types of OOV term. New adopted rule attend extraction system is used to solve the Hebrew translation problem. Our method achieve high accuracy in the experiment. Thank you very much.
So thank you. So is there any question or comment from audience? I have one short question. First, you predict the type of the OOV term that is name type and it is
Yes.
so what is the accuracy of the prediction? You may show
Result exactly.
very high.
Yes, because we believe because the experiment is conducted not on a very large data set. So, and as we extending the work and we could see the result good and we're improving the method.
You predict the type based on the word rate.
Yes, according to the context information.
But what is the main cause of the errors of the type prediction? What is the main cause of the errors of the type prediction?
I don't get it.
Why prediction sometimes fails?
Because it failed mostly due to that certain terms does not extract the definition. For example, mostly because of the biomedical terms, they have little information on the internet. Sometimes the extracted definition is actually not as a definition, it's like a web page that has many OOV terms and it only provides a translation. So in that case, the terms extracted from the definition according to the automatic tree from the WordNet does not provide the correct information and then it will fail.
Thank you.
Thank you.
Yeah, any other questions? Yes, please.
So thank you very much for your nice presentation. So I have one question about usage of the WordNet. So for example, in WordNet there are many synsets, and if you choose the wrong synset, then maybe it will produce a wrong translation. So how did you handle that?
Yes, because in the WordNet actually when we extended the automatic trees, the tree is very deep. So what we do is basically we select some supernode terms and then we only use a brief hyperlinks only. So we do not go deep into the and it sometimes provide some disaggregation. For example, sometimes it provide the tree that can cross into another class. However, due to the fact that because we are comparing, we are not in this experiment we do not exactly tell that this will become the person or company, but we only classify into biomedical and name type. So far it is successful on this stage.
So I have another question, which is kind of like, for example, when you are translating a OOV word with some extra information using the hypernames, so you are saying that as semantic translation. So, for example, if we use this, what is the application of your system? Is it in machine translation or?
I'm not not sure to get your question correctly. The word name here we only use for the prediction of the types of OOV term, and we extract the semantic meaning of the term. The translation is conducted